Hello friends, this is a video on the energy forms in fission and fusion. So during fusion and fission processes, the products are more bound, so they clap together. Clap. Strong force activates. What we haven't talked about yet is that this creates an excited nucleus, although we will talk about it in class, of course. What an excited nucleus is like, remember, protons and neutrons are like waves. So they are like electron orbitals. They can be excited. You can have a second harmonic nucleus or a third harmonic nucleus. So if I wanted to, right, I could add energy to a nucleus and it has like this vibrational energy to it. I could make it more energetic. I could have an excited, right, second harmonic nucleus where I think the nucleus actually physically grows a little bit, just like the electron orbitals, and they vibrate. They're a little more energetic. And what happens is that's an unstable situation, and it'll actually return back down to the ground state. Just like electrons did when they returned to the ground state, if you remember. An electron would return down to the ground state and emit a photon. Same here. They'll return down to the ground state and maybe emit a photon, or maybe emit an electron, or maybe emit another proton or an alpha particle. Here, for electrons, the only option was light. Here we have three options. Let's go through them. That's the picture. The first option is that the energy stays in the strong field and the quark field, right? So via the strong force, the energy will stay in the gluons and the quarks and will manifest as a release of a proton, neutron, or alpha particle. That manifests as heat. What is heat? Heat is excess kinetic energy crashing into its environment, crashing into the surroundings. So if we have a bunch of particles in a box, and you notice if I turn on the heater here, what does it do? It makes the bottom molecules go faster, which if you follow one, it then collides with another molecule, and that kinetic energy eventually spreads into the room. This is what we call temperature. So if you increase the kinetic energy of one of these balls, it'll actually collide into another ball, and that kinetic energy will distribute on average throughout the entire room. So if I make one of these air molecules in the room, look at the air in your room, imagine it, look through it. Look, imagine there's a molecule there and you push it. Say you were to push it. Even pushing my hand through it actually adds kinetic energy to the room, actually heats up the room just a little bit. Just a little bit. So adding kinetic energy actually heats up a room. That's what heat is. It's kinetic energy which converts to temperature. So if you read all of my words exactly, I hope this makes sense. This is the most probable where the energy stays in the strong field. Now, if the nucleus has an imbalance, criteria for this is you need enough energy, though, to strip away a proton or neutron from the excited nucleus. Typically, you have enough, but sometimes you don't. So that is important, and we can calculate that. I'm going to have that as a bonus question on the homework. You can just look at the binding energy, right? How much is one proton stripped away? How much energy does that take? And does my excited state have that much amount of energy? I know how much energy because I calculated that clap, right? I calculated the amount of energy released. Well, the amount of energy released, the point is stored inside the excited nucleus temporarily. Now, this is like a fraction of a second, right? It's activating, And the energy is stored inside the excited nucleus and then gets transferred to other fields when the excited nucleus returns to the ground state. So the energy is stored in here, and then it goes to these other fields. If it's enough to strip away a proton or neutron or an alpha particle, it'll do that. It'll do it first, most probable. If it's not, or there's an imbalance of protons and neutrons, remember, too many protons, what's the issue? Too many protons, too much electric repulsion. Too many neutrons, what's the issue? Pauli exclusion principle. Well, the universe has a solution for that. It's called beta decay. And it's when a proton turns into a neutron via the weak force, or when a neutron turns into a proton via also the weak force. So this is via the weak field, via the weak field. So the neutron, you actually have two ups and a down. The down quark through the weak field turns into an up quark plus an electron and a neutrino. Technically, this one's an anti-neutrino. No big deal. Right? And this weak field, right? And I believe this one is a W minus boson. The bosons are doing the work. That's just a name for where the energy goes through. To transfer information from the down quark field to the up quark field and to the electron field, which remember are all in the same place at the same time. I have a wiggle in the down quark field for it to go into the up quark field and then go also into the electron field. I need it to transfer. How does it transfer? The weak field is that information carrier. It's the one that carries the energy to the fields. It's the one that bridges the gap. The weak field is the connector between fields. So is the strong field, so is the electromagnetic field. The weak field causes energy to transform from one field to another. It's a transformation agent. Without it, protons couldn't convert into neutrons, and neutrons could not convert into protons. It wouldn't happen. This weak field is the force that does that. It's the connector. What's a force? A connector. It's the connector and transfer of energy from one to the other. This is the second most probable. Pause and rewind that if you want more clarity. I think I explained that pretty well. I hope it made sense. The third possibility is that it goes into light. Now this is the least probable because EM is the weakest force. The weak force is stronger than the electromagnetic force, but it's much weaker than the weak force. So it's called the weak force because it's all relative, isn't it? But the electromagnetic force is actually the weakest of the three. And so the connections are a little weaker, so it's least probable, and it only happens when neither of the other options are possible. So if you have an imbalance of protons and neutrons, the universe will correct it via transformation. Great. And I'm going to go through some examples in a second. If you have enough energy to release a proton or neutron and give it the extra energy, and then it collides into the rest of the room and it bounces around, cool. That's what we mean by heat. If not, then it'll go into the electromagnetic field and it'll release a high energy photon. That's a lot of energy still. It'll release a high energy photon, most likely an X-ray or gamma ray, typically a gamma ray. High energy light. Great. Criteria: when neither of the other options are possible, meaning when there isn't enough energy or when there isn't an imbalance of protons and neutrons. Great. Here's what it looks like: excess kinetic energy bouncing around. That's heat where it stays in the strong field. Beta decay, notice 6 protons, 8 neutrons. That's too many neutrons for a carbon atom, so the universe balances it by releasing an electron, and we have one of those neutrons turn into a proton, becoming nitrogen. We call that beta minus decay because it's an electron. 6 protons, 4 neutrons. Too many protons. I need to release a positive charge. A positron goes away, and the weak field transforms a proton into a neutron. Now it's boron 10. Great. Balanced. Nice. Right? So this is balanced. Now be careful when you get big, when you get to like gold or platinum, right? Or these bigger nuclei, big nuclei, balanced means something different, right? Balanced means you still have more protons than neutrons, right? So you can still be balanced with expect more neutrons and still be balanced and still have balance. So for each nuclei, what balanced means is different. So if I have gold, I think 147 is balanced, but gold 148 is not, and it will go through beta decay. And we'll turn one of those, I believe it'll turn a neutron into a proton, and it will become 147, and whatever one proton is less than gold. And I don't happen to know what that is. I actually believe that is platinum. Kind of fun. I think that's right. I don't know if I made that up in terms of the numbers. I didn't make up the process. I hope I didn't make up too many numbers. The point is, I hope I didn't make up wrong numbers. I remember these being the numbers. It's okay. Apologies if they're not. The point is, you can have this then release a positron and a neutrino via the weak field. It'll say, okay, I'll help you find balance, and then that might be balanced. Although I'm actually not sure if that is also balanced. And then it'll decay again until it finds the balance that it wants. That the universe then says, okay, this feels balanced in terms of the forces that are at play. So if neither of those can happen, then it goes literally into a gamma ray. We call it the parent excited state. Fusion happened here first, or fission. We'll say fusion happened here first. You have two things collide, boom, clap. Now we have that energy stored for a fraction of a second. The energy is stored in the excited state and then is released either via excess proton or a neutron flying out or an alpha particle flying out. Boom, released, it can collide. This will also have some kinetic energy because it's releasing something. Imagine being on a skateboard and you throw something, conservation of momentum, right? Means that one thing goes one way, one thing goes another way. Change colors, it's all good, right? So this is actually, I'm going to erase this. This should actually go off in the other direction, where we have this go this way if this goes this way by conservation of momentum, right? Because this gamma ray has momentum in this direction, P equals H over lambda. So therefore this will have momentum and kinetic energy in the other direction, P equals mv. So this will then collide with something as well and manifest as heat. Examples, you ready for it? I hope that made sense. That's the concept of what's happening on a nuclear level. Fission alpha decay of 183 platinum into osmium and helium. My gold was way off. There's no way it's 147. I should have been more grounded in those numbers. The concept was right on, but no way that was gold into platinum. Sorry, I made that up. Because platinum is, 183 is unstable. It will decay into a helium atom, helium nucleus, and an osmium nucleus. Great, this is fission. Now these have excess energy. These products are not excited though. I want to start by saying not always does this happen. Like I said up here, it only sometimes creates an excited nucleus. Pretty much it's always for fusion, but sometimes fission, right? But fission, what you get because you're ending up with smaller things, they typically just carry it away as kinetic energy already. Imagine a platinum nucleus that's here, and then it becomes, right, an osmium nucleus and a helium-4. Well, the helium-4 is going to fly at some velocity. The osmium is going to fly at some velocity, where it's literally like the platinum shot out like threw a ball really fast, and therefore it goes back like it shot a cannon. And there's the recoil going the other direction. You have kinetic energy of both of these going off. The recoil nuclei will contain that energy. Great. Example number 2, deuterium and tritium fusion. 2 + 3 is 5. You actually get, remember we did this in class? There's a secret to the arrow. The arrow that once was here secretly contains an excited nucleus where that energy is stored for a fraction of a second. The energy is stored in this excited nucleus for a fraction of a second, and then that excited nucleus is unstable, and there was enough energy to remove a neutron from it, so it released into 2, once again, same idea. You start with a helium-5, and you have a neutron and a helium-4 ejected in opposite directions. The neutron goes faster because it's heavier. The helium-4 goes slower by a factor of 4, right? Because it's 4 times as heavy, 4 times as massive by conservation of momentum. M1v1 equals M2v2 to conserve momentum. Just because the total momentum is 0. It started out with just a helium-5 in place, and then boom, they went in opposite directions. See what I did with my hands? Boom, opposite directions. One goes faster, one goes slower because the lower mass goes faster by the same proportion. That's it. Kinetic energy turning into heat. Kinetic energy turning into heat, turning into temperature. That's what that means by heat is released. Now here's an example where light is released, number 3. Say I have proton plus deuterium to an excited helium-3. That contains the excess energy. Is in the excited state. That's what that means. Well, that excited state, it's stable. It didn't have enough excess energy to remove a proton or neutron, and it's not imbalanced. He3 is stable. 2 protons and 1 neutron, you might say that's a 2-to-1 ratio, but it's a strong nucleus. That for it, that's normal. That's a normal balance of protons and neutrons. From what we're talking about, electric repulsion, strong force attraction, it's small, it's tight. The strong force says, I got this. It's not unstable. So stability is what we're looking for here. If it's stable, it just turns that energy into the electromagnetic field. So no beta decay, it just emits a photon. Boom. So that's why we get a photon here, is because beta decay and the emission of a neutron or proton were not energetically beneficial or possible. Cool. That's the concept of these forms of energy. Stay tuned for a video on calculating these numerically that I'll post next. Thank you, guys.